Hello all, welcome to our next session in transportation engineering. I hope we have seen the previous sessions. So under transportation engineering we are under highway engineering. Under highway engineering, so if you remember, we have discussed 4 chapters. We are under the chapter 2 of geometric design. Under geometric design we are on the last topic called valley curve. If you are continuing from the previous session, it will be easy to follow up. So the valley curve, as it is the opposite of the summit curve, this convexity will be downwards. Okay, you can see the shape of the valley curve. You can see the drawing I am drawing. So everything all look like a cup shape, or we will even say it is also called as a sag curve. Sag means, if you remember, in strength of materials we have seen, it is a shagging, correct? Hogging and shagging. Cantilever will bend in the shape of hogging. Simply supported will bend in the shape of a shagging. Okay, so this shape gets the name from there, sag curve. Okay, so if you remember, we have seen the deviation angle, how you have obtained for the summit curve. Here also you can use the same formula, n1 minus n2. How much the gradient 2 is deviating from the gradient 1. Okay, so based on whether it is a rising gradient or falling gradient, you can use either plus or minus for this also, plus or minus for this also. Okay, so using this formula, try to pause the video and try to determine the deviation angle for different cases. Here there are 5 figures I have given you. So you can see from the case 1, for the case 1 it is very simple, minus n1 minus n2. Okay, one rising and one falling, one falling and one rising. Okay, so you see this case, this is minus n1, again plus n2. Okay, you can pause the video and think why it is coming. It's very simple, just plus or minus. Okay, so next video, if you see n1 minus n2, and this n2 is 0, so this is just minus n1, and this you see n1 is 0 and plus minus n2. So mostly you see we are getting a negative sign. Summit curve will never go to negative sign. Okay, so valley curve you will expect either small values of positive, or most of the case we will get as a negative answer, but don't use that negative answer in the formulas. Okay, so the negative answer says that it is acting in downward direction. It is just a directional point of view. It's showing you how the direction is. Okay, where the direction goes, how, in which direction the deviation is happening. Okay, so I hope I made you clear the deviation angle for the valley curve. And if you see the table, horizontal curve we have seen during the super elevation, we assumed it as a shape of an arc of a circle. For transition curve, if you remember, we have assumed it as a spiral shape. For summit curve, if you remember, we have assumed it as a square parabola. For valley curve, we assumed it as now we are assuming it as a cubic parabola. Okay, so y equal to a some constant into x cube. So for different x value, we will have different y value. You can pause the video again. If you are having another tab nearby, means like a browser, you can open it, y equal to x cube curve, how it will look like. Okay, so that shape we are going to adopt in our road. Okay, in our highway, for a valley curve we are going to adopt a y equal to x cube curve. A is a constant, will be a function of deviation angle and length of the valley curve, that we will see in 1 or 2 slides. Okay, so one of the prime problem we are going to face, give me 1 second, I will draw this one. Weight of the vehicle will act downward. Also, because of the curve, the centrifugal force is going to act downward. Okay, so one of the prime difference from the summit curve, the valley curve is going to face is the impact. When you are moving in a valley curve, obviously your vehicle will go out of control from your because of the centrifugal force is going to make your vehicle, and also weight will also help. So both will be acting downward direction, which will create a impact on the wheels. Okay, so it will create a discomfort to the passenger. So we should provide a length of the valley curve such that our rate of change of centrifugal acceleration, if you remember, mv square by r was the centrifugal force, right? That v square by r is the centrifugal acceleration. We should provide a length of the valley curve such that the driver will not feel any discomfort. Okay, so this is one of the prime factor in deciding the valley curve. Second factor, we won't have any issues of sight distance, right? When you are traveling in a valley curve, so you can easily see the opposite vehicle, but only in the daytime. In night time, you can only see their headlight. The headlight will create an issue. Actually, it will create an issue when you are traveling in a valley curve. So you won't clearly judge based on the light source. You won't clearly judge where is the source is from. Okay, so you lose the time in judging the headlight source. So that what they have decided, so the design factor they have included, one factor is you should consider the impact free moment, and second they have included the headlight side distance. Okay, so length of the valley curve will be based on maximum of, you find the one length based on centrifugal acceleration, one length based on your headlight side distance. So you will provide the maximum value. Okay, so this will be the length of the valley curve. Okay, and another assumption, very important thing, what our IRC suggested is, you can take it, if you remember the length of the transition curve, if you remember the story of transition curve, there was straight road, there was a horizontal curve. Okay, and the green color what I am drawing now is the transition curve. In our highway we assumed it as a spiral shape. For railway we will see in some of the videos, in coming videos you will see that for railway they have assumed as a cubic parabola shape. So if you see the spiral shape, it is a semi, right? So it's a half, like a quarter circle, right? So since it is a cubic parabola shape, can also be adopted for a transition curve. What IRC is suggesting is, so instead of, you can even assume length of the valley curve as 2 times. So you can see the figure above, it will come something like this, right? 2 times of the length of the transition curve. So this is one of the major assumption, because length of the transition curve will be provided, if you remember, to have a constant rate of change of centrifugal acceleration. If you remember, we have maintained a rate of change of centrifugal acceleration as a constant. That's how you got, if you remember the formula, V cube by CR, correct? So what IRC is suggesting is, so this will be a quarter arc, so provide the twice the arc, so that the rate of change of centrifugal acceleration can be also maintained a constant. Okay, in this throughout the valley curve. Okay, so from this slide what you should understand, the valley curve will have a problem in the impact force, which is not there in the summit curve. Point 1. Point 2, what you should know is, so although the side distance will not be a problem, headlight side distance will be a problem. Okay, so the length of the valley curve will be maximum of one length you will get from impact free like centrifugal acceleration maintenance, and the another thing you will get from a headlight side distance. Okay, so provide the maximum, that is a point 2 you should know. Point 3, what you should know is the length of the transition curve, how you calculated, like V cube by CR, you can provide the twice the length as a length of the valley curve. Okay, so 3 points you should know. Okay, so it's like a summary. If you understand, we are going to provide a cubic parabola shape, y equal to ax cube. Some a is a constant, don't think a is some radius or something, it's just a constant. So then you should know headlight side distance will be another criteria, and motorist comfort will be one criteria. And also the third point you should know is, valley curve we should consider as a serviceability condition. Drainage will be an issue, right? Okay, so you should, which was not a problem in summit curve, you should consider as a serviceability criteria. The drainage will be an issue, so you should think of a proper gradient, or you should think of a traverse gradient, how to drain the rainwater which is about to get stored in the valley curve. Okay, so you should have some drainage control also. So, and also it should be aesthetically pleasing. So keeping all this thing in mind, we are going to inside the design. Okay, so again I am telling you, length of the valley curve will be maximum of LV1 and LV2. Okay, so if you see this is a formula for LV1. As I told you, it is twice the length of the summit curve. If you remember, length of the summit curve we can write it as V cube by CR, right? And if you remember your school mathematics, we will say arc length, any arc which is cutting, we can say the arc length as r theta if the theta is very small. Okay, so bringing the same story to our valley curve or transition curve. Okay, so this angle, n is a angle, right? So far you know n is a deviation angle. Okay, it is how much two gradients are deviating, and you know this is the length of the transition curve, this is the radius of the transition curve at any point. Okay, so from this what you can write, length of the transition curve can be written as Rn. So radius can be written as Ls by n, correct? So bring that radius equal to Ls by n here. So ls can be written as v cube by c into ls by n. So when you do some small algebra, you will get ls equal to square root of v cube n by c. Okay, so length of the valley curve is twice, right? So multiplied by n value, the 2. Okay, 2 in front of the square root of n v cube by c. Okay, so you got this formula 2 into square root of n v cube by c. So also they are asking you to maintain a constant c value. Okay, because you know what is c, right? Rate of change of centrifugal acceleration. So you have to maintain this as a constant. So that's why meter per second square per second you should maintain. So having this in mind, you can determine LV1. Okay, and similarly this is the value you will get when you are substituting the boundary conditions, and you will get this value. If you remember, in summit curve we have derived this equation for a square parabola. Here it is cubic parabola. It will be a huge steps to derive. You can check the derivation if you are interested in Khanna and Gustav book. Okay, so this constant you can use it for plotting. N is the deviation angle, L is the length of the valley curve. So if you know these two, you can use this equation to plot the valley curve in the site. Okay, so hope from this slide, I hope you have understood how to determine the length of the valley curve based on a comfort criteria. Okay, 2 into square root of nv cube by c, where c is 0.61 meter per second cube, v is in meter per second. Okay, v is in meter per second, n is the deviation angle. Okay, so second criteria is, I already discussed, it is LV2 is based on headlight side distance criteria. So consider a straight vehicle. Okay, consider this is the tires, and consider there is a headlight is here. Okay, so distance of the headlight center to the ground is the h1. Okay, and angle is alpha. Okay, angle is a headlight beam angle. IRC has suggested the angle is 1 degree, and h1 is the height of the headlight from the road surface is 1.5 meter. So IRC has given this empirical formula, or you can even derive how it came. You can see this figure, and then from this figure you can pause the video and try to understand that figure. I have zoomed it here. You can see same S tan alpha plus h. From there only they got this formula, 2 into h1 plus 2 S tan alpha. Give me 1 second. Yeah. So 1.5 meter plus 0.35 s will give you the denominator. N square, you know, s is the side distance, and you remember overtaking will not be an issue in overtaking headlight. Sorry, in valley curve it's very easy, but only the issue is headlight side distance, right? So we will have only one case: length greater than side distance, length lesser than side distance. You substitute that h1 and tan alpha values here, you will get this equation. Okay, n square divided by 1.5 plus 0.035 into s. Similarly, you will get L is equal to 2s minus 2h1 plus 2s tan alpha divided by n. So when you substitute that value, also you will get this second equation. So both are, these are LV2. Okay, based on the side distance value, you can assume either case 1 or case 2. So from this slide, I hope you understood what is the headlight side distance assumption IRC has made. It is 0.75 meter as a height. Okay, and what is the angle of beam? It is 1 degree. Okay, substitute that value in the empirical relation, you will get the formula n square divided by 1.5 plus 0.035 into s. So if you know the two cases, when length is greater than SST1 formula, when length is greater than lesser than SST1 formula. So from this slide you will have the formula for LV2. So from the previous slide, you know LV1, you will provide the maximum value. Okay, so some of the notes you should know. As I told you, OST will not be any problem, and location of the deepest point in the valley curve. So if you want to find the deepest point, where the deepest, always it no need to be symmetrical, right? Always, everywhere valley curve no need to be symmetrical. You have seen in the first video, when the video started, I showed you 5 different kinds, right? So where the deepest point is can be determined using this formula. Okay, so if you are preparing for some IES kind of exam, so this they will ask you even to draw in a conventional paper. So conventional question they will ask you, so you should know this formula. N1 is the gradient of first gradient slope, L is the total length you got from above, and N is the deviation angle. With that you can determine where will be the deepest point in the valley curve. Next point you should know is impact factor. If you remember impact factor, mv square by r, we have used this term in super elevation. Mg, you got v square by gr. Okay, from the radius you can write as a L by n, all those things you just convert into a unit. So finally you will get this equation doing some algebra. Okay, so this will be the impact factor calculation for a valley curve. How much will be the impact coming? Okay, 1.6 NV square by L, and the answer should be less than 17% as per IRC. Okay, this is very common to ask. You should note this as a also as a formula. Okay, so hopefully I have given 5 formulas here. One is plotting the valley curve, one is LV1, one is LV2, fourth one is this location of deepest point, fifth formula is impact factor. Okay, so you can pause the video, take your formula sheet, note down these 5 formulas with all the terminologies before coming into the problems. Okay, so question number 36, you can pause the video and solve yourself. Okay, so then you can come back to the answer. Anyway, I will discuss here. A valley curve is formed by a descending gradient. Okay, so there is a descending gradient of 1 by 20 meets an ascending gradient of 1 by 30. So they have given the descent speed and also the allowable rate of change of centrifugal acceleration. They are asking length of valley curve for comfort criteria. So it is they are just asking LV1. Okay, so I hope you remember. You just convert step 1 kilometer per hour to meter per second. Okay, and if you remember the formula n1 minus n2, here they have given n1 itself descending gradient, right? So minus 1 by 20 minus n2 is ascending gradient, so it just you can keep it as a positive, so you will get this value 0.083. okay, so if you know the formula, length of valley curve is twice the length of the transition curve, which is nothing but nv cube by c. Yeah, you just substitute everything here, you will get 77 meter. Okay, which is nothing but option B. Okay, so quite simple, direct formula substitution. So next question, a valley curve is to be descended for a national highway in a rolling terrain where a falling gradient is given, meeting a rising gradient of 1 by 20. Descent speed is also given, c is given, and SST is given. So they are asking the length of the valley curve, first question. So you should know, calculate LV1 and LV2, provide the maximum. Okay, second they are asking the impact factor. So using that length of the valley curve from above, you substitute here, you will get the impact factor. So you can pause the video and solve yourself and come for the answer. So here n1 is 1 by 25 they have given, n2 is 1 by 20 is given, v is given, c, SST is given. So step 1, determine the deviation angle. So minus 1 by 25, it is falling gradient, so it should be minus 1 by 20, you will get minus of 0.09, but as I told you, you no need to use minus, it is just for a what directional point of view. Okay, you just need the value, how much it is deviating. So step 2, I will assume length of the valley curve is greater than SSD. So assuming I substitute here, I will get 373 meter. So 373 meter is obviously greater than 180 I am getting. So my assumption is correct. Okay, so I got LV, actually it should be LV2. I got LV2. Step 3, use the formula, it should be 2 into square root of NV cube by C. You substitute the N value, V in meter per second, C is 0.61, you will get 114 meter. So this I got as the LV1. So length of the valley curve should be maximum, right, of LV1 and LV2, right? So what, 114 and 373. So maximum is the 374 meter. This is the answer we got for the question number 37, 374.62 meter, option C. So using that answer to determine the question number 40's answer is, question number 38's answer is impact factor 1.6 of NV square by L. N we know, deviation angle 0.09. Velocity, this is in kilometer per hour. Remember, we should substitute in kilometer per hour. Length of the valley curve value, you can directly substitute that, you will get percentage in 3.85%, which is somewhere here. Okay, always remember, you cannot match exactly with even second or third decimal, you find the nearby value. See, 373 I know, so I substituted 374 as an answer. Okay, maybe you don't know what was the second decimal, third decimal they used to calculate the answer, so which is nearby, you can use it as a answer. Okay, so this question is an assignment for you. A falling gradient of 1 in 20 meets a rising gradient of 1 in 40 and MDR in a plain country. Okay, so the descent speed is 80 as given, SSD, same question, exactly same question, impact factor, everything. I have given an answer also. Okay, you can note the answer also. You can solve yourself and compare your answer. If you have any doubt, you have my mail ID, you can mail me anytime. Okay, so this completes the geometry design topic. You can see this complete geometry design topic of highway engineering. As I told you, if you take any question paper in civil engineering, at least one question from the coming from this geometry design, whatever you have seen, from super elevation, from side distance, or summit curve, valley curve, setback, and everything. Okay, so try to solve we have solved around 40 problems, I think, approximately 35 to 40 problems in the geometry design chapter itself. So you try yourself to solve at least 200 to 300 problems collecting from everywhere, so that the geometry design chapter you will be an expert. Okay, so at least you will ensure 2 or 3 marks, like 2 or 3% in the any question paper whatever you are preparing. Okay, so thank you. We will meet you in the next session for highway materials. Thank you.